Our third and final video of the day has everything to do with what's called correlation coefficient and determining the strength of a linear association. So it's going to look familiar to something that you did in middle school. Has everything to do with scatter plots. So scatter plots can be used to show relationships between two sets of data, right? All the little dots on the screen, right? They could be distance and time, revenue and number of items sold, or other pairings of two variables. Okay, some scatter plots, they might have a positive linear relationship, which means the graph is going to go upwards. All the dots generally go up. Some scatter plots have a negative linear relationship, which means the dots, go down like a negative slope. And others just simply have no linear relationship whatsoever. So that's when the dots have no trend and it's like all over the place. Okay, now this can be measured, this strength, this direction, in what's called a correlation coefficient. A correlation coefficient is represented by the letter R. This is a statistical measurement that measures the strength of a linear relationship. It might be super strong, which means the points are really close to each other. It might be weak, which means they're going up, but they're kind of spread out. This is a value between -1 and 1. So we're just measuring it as if it was, between -1 and 1, positive or negative. Okay, let's talk about these things. So if we see here, we have our differentiation between -1 and 1. If the R value, if the correlation coefficient is -1, that means that it is a perfect negative correlation. It means the graph would go literally down in a straight line. As we get further and further into this graph, it's still going down, but maybe not as tightly aligned, until we get to the point where we have no correlation whatsoever. Okay, it's not strong, positive, it's not weak, negative, it's just like zero. There's no relationship between points. Until we get all the way over, getting closer and closer together in the positive direction, okay, till we get to that perfect positive correlation where the dots are in a perfect straight line. Okay, our linear equations that we've been dealing with, y equals mx plus b, where m is like a solid number, are perfect positive correlations. But they're not always going to be that perfect, because when we deal with real life data, it might not be a perfect 3. It might be a little bit off from 3. So values of R close to 1 or -1 represent what's called a strong correlation, because it's close to 1 and -1. So these two right here are strong. One of them is strong and positive, the other one's strong and negative. While values of R closer to 0 represent no correlation, which is what we've already talked about. So we're looking for strong correlations for the numbers to be close to 1 or -1. Like if they would round up to 1, they're probably a strong correlation. If they wouldn't round up, they're probably a moderate, if not weak, correlation. Now this gets into some real statistics here if we talk about when it becomes moderate, strong, and weak, but we're just going to know if it would round to 1, round up, 5 or more raise a score, we're going to call that strong. 4 or less, let it rest, we're going to call those weak. Okay, so the way that we find this, again, is going to look familiar. We're still going to make our table and input all of our points and write the fancy version of number 9, right? That's the equation number 9, but fancy. And instead of looking at the m and b, which I found when I was writing the linear regression, I'm looking at this R value right here, because correlation coefficient is an R value. If we were trying to put the R value of 0.155 on this number line, 0.155, first of all, is a positive number, and it was probably going to be somewhere in here. So we'd call this a weak positive correlation, because it wouldn't round up to 1, it would round to nothing, round to 0, it would let it rest, so it's a weak correlation, and it's a positive number, so it's weak and positive. So we're just looking at that R value in the statistics part of Desmos that tells you what the correlation coefficient is. whether this data is super strong or like kind of weak. Okay, so let's see some examples here. Oh, it's on my next page. It says, interpret the correlation coefficient to determine the strength of the linear relationship. So you can kind of look at the dots on the screen and kind of see what's going on. But if you look at the correlation coefficients here, this is 0.855. That would round up to 1. So this is a strong positive correlation. And that makes sense to me because look at the graph. It's a positive slope. It's going uphill, and the dots are generally close together. If you look at the next one, this is going downhill, and because the number is negative 0.721, would round to -1, so this is a strong negative correlation. The graph's going down, but that correlation coefficient, R, on my number line, would be closest to strong negative as opposed to weak negative. If you look at this last one here, its correlation coefficient is negative 0.018. Now, that's not exactly 0, so it's not like there's no exact correlation, but like these dots are not close together. Like I'd have no chance of drawing a straight line between them. So we're going to call this a weak, but a weak negative. Now, why did I say weak negative as opposed to weak positive? Yeah, I can't really tell from the graph, but if you look here, that number is negative, so it's a weak negative correlation. All right, let's find our correlation coefficients and interpret them. In example 1, it says, the table shows the durations in minutes of several eruptions of the geyser Old Faithful, that's in Yellowstone National Park, and several times y in minutes until the next eruption. What does the correlation coefficient for the data indicate about the strength of the linear association between durations and times? My key words here, we should circle, star, underline the words correlation coefficient. And as a hint, look for the word strength. We're going to try to decide if this correlation coefficient is strong or weak and positive or negative. So let's follow the steps on the other side of this page. We're going to add a table to Desmos. Type in all of the points. Do you have to type in all of the points, or can you just pick a couple? No, yeah, you have to type in all of the coordinate points. Take a second, make sure you have them all in there with no typos. And I'm going to click the Zoom Fit button so I can see that information, even though my face is kind of covering part of it. There we go. Then we need to write the fancy version of equation number 9. This is going to be y1 squiggly line mx1 plus b. A bunch of stuff pops up. Now, we're not interested this time in these m and b parameters because we're not writing a line of best fit or trying to decide what it is in the future. We're not trying to predict anything. We just want this r value here, 0.9787. So that's my correlation coefficient. The r is equal to 0.9787. Now, easiest part is to determine if it's positive or negative. Obviously, r is a positive number, so this is a positive correlation. Also, the slope, like literally the slope's going up, so it's positive. But we just need to know if 0.97 is closer to 1 or closer to 0. Very obviously, it's closer to 1, which means it's strong. That number would round up. So it's a strong positive correlation between the duration of Old Faithful's eruptions and the time in between its eruptions. Let's look at example 2. And since I'm switching examples, I'm going to go ahead and get rid of all of my stuff in Desmos, get a clean Desmos, and press home. Okay. The table shows the weekly sales of a DVD and the number of weeks since its release. What does the correlation coefficient for the data indicate about the strength of the linear association between the weekly sales of DVD and number of weeks since its release? Okay, again, my keywords here are correlation coefficient, and the additional hint, if you forgot what that means, is strength. We're looking for the strength. We're looking for that R value. I'm going to go ahead and add a table and put in all of my numbers. Can I skip any of the numbers? No, that will change my R value. I have to use every piece of data possible to get this to work. I'm going to still press the magnifying glass so I can see the information. And then I want to say y1 squiggly line what am I typing? y1 squiggly line mx1 plus b. And we have our line of best fit that has been drawn, which we're not really that worried about. We need the correlation coefficient, that R value. Now this makes a lot of sense to me because if I hide this for a second, look at how tightly together and negative going downhill those dots are. So it makes sense that my correlation coefficient is negative 0.9833. One, that it's a negative correlation and that they're super tight together. This number would round up to 1. This is a strong negative correlation. The dots are super close together as if they were on a straight line. So it's a strong as opposed to weak. And then this one's negative because it's going down. Okay, we have to know how to utilize these R values to determine the strength of data. This is how you make sure when you're given a piece of information in statistics that it's actually worth measuring if that data is super strong, and that means your correlation makes a lot more sense in real life. Correlation coefficient, R value.